Okay, so it's recording now. Welcome everyone to part 2 of lecture 11 of the course Quantum Theory in a Nutshell. So before the break, we were discussing on how to write the expectation value of an observable in a state U. And I introduced these operators pi that were used to construct the operator A hat, which is the operator associated with an observable. This pi is constructed out of the outer product of vectors that have a well-defined measurement value. So I know if I measure the observable A on a state EJ, I know that the value that I'll get will be AJ. So the operator pi has the property that it is constructed out of those states. As you're going to see, these operators, they have a specific name. They're called projection operators. And they play a very important role in the mathematical framework of quantum mechanics. Okay, so far I told you some postulates that first tell you what is the mathematical device that you use to describe a quantum system, and this is a vector. So this is a state that is represented by a vector in a vector space, in a Hilbert space. And postulate 2 tells you how to compute the probability of measuring a value AJ of a quantity A, given that you know what is the state of your quantum system. But of course, we also want to have a prescription for the definition of observables. I mean, I just told you that A is a quantity that is an observable. Now I defined an operator associated with this quantity. So, and this operator was kind of defined, you know, by hand. But is there a general prescription on how to define an operator? And if so, what are the good properties that such an operator must satisfy? So this is what we're going to start discussing now. Okay. So I'm focusing on polarization. So if so, I have two states that I'm writing as EJ or EI that have a well-defined polarization, in the sense that if I have a measurement of a quantity that just depends on the polarization of the photon, if the state is one of these two states, E1 or E2, then the value that you're going to measure is always the same, okay? But as I said, I mean, a system typically will not be in one of those states. Typically, when you make a measurement, you're going to get different outcomes, okay? So how to represent a generic state? Well, if we're talking about a two-level system, and you know that those vectors EJ, they are normalized and orthogonal, then you can construct an orthonormal basis for this vector space. So any vector that you want to think about, let me call it C, that describes the state of a quantum system, can be written as a superposition, okay? Pay attention to this word, a superposition, which is nothing but a linear combination of E1 and E2. So this generic state, C, is nothing but the linear combination of E1 and E2. And the coefficients that you have here C1 and C2, they can be computed by the projection of this vector C along the directions E1 and E2. So if I take the scalar product of the vector C with E1, then I will hit these cats with E1, and you're going to have E1 times E1, and this is 1 by definition because this is normalized, and then you're going to have E1 times E2, but E2 E1 times E2 is 0 also by assumption, because I'm assuming that E1 and E2 are orthogonal. So there is a question in the chat. Did we multiply by C? No, I'm multiplying by E1 on both sides, okay? So if I multiply by the bra E1, you see that this first term will become just C1, because E1 times E1 will be 1. And the second term will disappear, because I will have E1 times E2, which is 0. Okay? So what I'm seeing is that C1 is nothing but the scalar product between C and sorry, I should be a bit more careful here, because so I'm just saying that I'm multiplying this quantity. Where is it? Okay. I'm multiplying this quantity by E1. Okay. So I had to have actually that C1 is, sorry, C1 is equal to this quantity. Okay. This is what I should have. And here I have the opposite. So to be more on the safe side, I should put a star here. This is correct, you see? Here I messed up with the order, so maybe I should correct that. Okay. So this will be E1 times C. Okay. Now it's correct. Okay, so let me erase that. Okay, so there is a question. Is the bra of E1 the same as the cat of E1? No, be careful. The bra of E1 is the transverse and complex conjugate of the cat E1. Okay? They are not the same. In particular, one is a column vector and the other is a row vector. So they cannot be the same. Okay. So just by contracting this equation here with the bra E1, I get who is C1. And now if I do the same with E2, the bra E2, I get C2. So this is how you extract those coefficients. Okay? That's very important. So those numbers, C1 and C2, they are, in our language, they are the entries of the column vector that represent C. C is so this is a cat, and therefore this is a column vector. So if I write C as a column vector, I would write C1 here and C2 here. And these cats E1 and E2, they form a basis. And if I am expanding my vector in this basis as being C1 times E1 and C2 times E2, and the column vector representation is C1, C2, then E1 must be the vector 1, 0, while E2 must be the vector 0, 1. So just take these two vectors, okay, E1 and E2, multiply E1 by C1. So you're going to have C1 in the first entry and 0 in the second entry. Now do the same with C2 and E2. You're going to have 0 in the first entry and C2 in the second entry. Now, if you add these two vectors, multiply by the corresponding c's, you get this vector, right? So this is completely consistent with what is written here, okay? So this is nothing but writing a vector in a basis, as you learn in linear algebra, okay? Now I'm going to look at the first thing we have learned about quantum states in these lectures, which is the quantum state associated with a photon which is linearly polarized in the direction theta. Okay? So we discussed that actually you can write this vector as cosine of theta and sine of theta. So for a generic linear polarization of a photon, you always write the state as in here, okay? Cosine and then sine. But of course, you see that there are two angles, in particular, theta equals to 0 and theta equals to pi over 2, that you reduce this vector to, when theta is equal to 0, this vector becomes 1 and 0. And when theta is equal to pi over 2, then you have 0, 1. You know that the vectors 1, 0 and 0, 1 are vectors that are, first of all, they are normalized. Second of all, they are orthogonal. So you have a basis to describe states of linear polarization of your photon. Okay? So your photon can have a linear polarization theta, and you can expand this vector in the basis of polarization 0 and polarization pi over 2. Okay? So this is what I'm saying in this paragraph. I'm saying that the vectors with theta equals to 0 and theta equals to pi over 2, they form a basis for any vector of any linear polarization. So if you have a polarization of 85 degrees, you can write as a linear combination of polarization 0 and polarization pi over 2. Okay? This is just a simple fact that comes from linear algebra. Okay? You have a complete basis. Those vectors are orthogonal, and they are normalized. So you have everything that you need for a good basis. Okay? So if I give you a generic state of polarization theta, then C1, which is the scalar product between the bra corresponding to the polarization 0 and theta, and C2, which is the bra corresponding to the polarization pi over 2 times the ket theta, will give to you the probability amplitude for you to measure the state theta that was prepared in the state theta in a state of polarization 0. And C2 will give you the probability amplitude of measuring the vector or the photon that was prepared in the state theta with polarization pi over 2. So this is, I'm just following postulate 2, okay? This is something that is very important. I mean, I'm just expanding a vector in a basis. But in quantum mechanics, the way that you expand the vector in a basis gives you information about the probability of finding the system in a given state that belongs to the basis that you used. Okay? So this is extremely important. And we also have discussed last week states of circular polarization. And we have seen that states of circular polarization are nothing but states that um, they can be written as vectors of norm 1, and that those states which we denoted by plus and minus, they are orthogonal. So they also form a basis that is such that the vectors of this basis are orthogonal and they have norm 1. So they form an orthonormal basis. So you can expand any vector. So for instance, you can expand the vector of linear polarization theta using the vectors of circular polarization. Okay, this is very important. So I'm just saying that I can change bases, and you learn that in linear algebra, right? You can use some bases to write down the coordinates of your vector, but you can use another basis to write down the coordinates of your vector. And this is what I'm doing here. In one case, I'm using the basis of linear polarization, and in the other case, I'm using the basis of circular polarization. Okay? And you are going to use the basis that is most convenient for your question. So if you want to ask what is the probability of finding this system that I prepared in a given state, in a state of circular polarization plus, then I better write the state vector as a linear combination of circular polarization vectors, okay? But if I'm interested in measuring the probability of getting my system in a state of linear polarization, I better write in the basis of linear polarization. So depending on the question that you want to ask, you're going to choose one basis instead of the other, okay? So here I am just telling you how to change bases, okay? I'm just saying, if you have the state theta of linear polarization theta, I can write it in the basis of linear polarized vectors. So what we call E1 and E2. And you know that the coefficients will be cosine theta and sine theta because those are the entries of your vector. But now I want to write the same vector in a different basis, which is the basis of circular polarization, which is polarization plus and polarization minus. And therefore, I want to compute what are the coefficients C1 and C2. Okay, this is a problem of changing bases in linear algebra. So in order to compute who is C1, I just act with the bra plus on the cat theta. So you see that the bra plus will hit the cat plus, and this will give you C1, while the bra plus will hit the cat minus, and this will give you 0 because they are orthogonal, okay? So you have C1 equals to, then you have plus acting on E1 and plus acting on E2. And you have to do the math, okay? So it's written here with some details that you can follow. Okay? Good. Well, you repeat the same for minus, for the polarization minus and theta, and you get another scalar. And therefore, you compute C1 and C2, and you can expand now theta on the basis of circular polarization, and you get those numbers here. Okay? And you see that if I ask you, given a state of linear polarization theta, what is the probability of this state to be measured on the state of circular polarization plus? And then you just have to look for the vector plus, it's here. Look at the coefficient, it's here. And use postulate 2. You just square it. You take the absolute value and square it. And you're going to find that it's half, as we have learned some time ago. Okay? So this is more or less how you are going to play with quantum systems. You have to find a way, you have to find a good basis to expand your state on this basis. And once you do that, it's just a matter of looking for the state that you want to make the measurement and read off the coefficient of this of this state. Okay? Good. As I said, this is a lot of information, a lot of new things that you're learning, in a very short amount of time. So you have to really read again, go through the arguments, and see if you digest the information carefully, because it's really a lot. Okay? And also that's why I'm concentrating for the moment on systems that are just two-level, because these things that I'm saying can be generalized for systems with infinitely many entries of the vector that describes the state of the system. And for the moment, this is just, this two-level system has all the elements for the construction of a theory, but it avoids all the complication of having to deal with much more complicated vector structure. Okay, so far, so good. I think I will ask you if you have questions before I continue, because you were quite silent today. So do you have questions? Okay, I don't see any questions. Oh, okay, so Seth is saying that, can you repeat once more? So you mean, okay, so I will repeat. Okay, so what we have discussed here is that a state with well-defined polarization is a state that will always give you the same polarization if you repeat the measurement over and over. Okay, and this will form a basis. So I have two vectors, E1 and E2, that they have well-defined, let's say, polarizations, in the sense that, if I make a measurement of a property that depends on the polarization, then I'm always going to make the same measurement. I'm always getting the same numbers. And what I said was, I'm just using a fact from linear algebra. So these vectors, they are normalized and they are orthogonal. So they form a basis. Okay? If they form a basis, then I can just express any vector of this vector space as a linear combination of those vectors. Okay? So I'm writing a generic state C that lives in this vector space as the linear combination of these basis vectors, so E1 and E2. That being said, what I'm saying is the following. I can, for instance, use the basis where E1 and E2 are just 1 and 0, and 0, 1. And if I'm looking at linear polarization, then these vectors, they correspond to the angles theta equals to 0, cosine of 0 is 1, sine of 0 is 0, so this is the vector 1, and theta equals to pi over 2, because cosine is 0 and sine is 1. Okay, so I'm choosing two vectors that are related to two particular angles, which is 0 and pi over 2. And by this statement here, what I'm saying is that all vectors, I mean, that represent a given polarization theta, can be expressed as a linear combination of polarization in the direction 0 and polarization in the direction pi over 2. Okay? And so I can write this vector as the sum of cosine times this vector and sine times this vector. This is just standard linear algebra. But if you don't follow what I'm saying, just let me know, okay? Because we can recap those things. Okay. But of course, you see that we also have learned that there are different states of polarization which are called circular polarizations. And we have computed explicitly the form of these polarization vectors in this basis. And we call those vectors as plus and minus. Okay? Well, first of all, those vectors, they are orthogonal. So if you go back to some old slide here, you have plus and minus. You can compute the bra associated with plus and take the scalar product with the ket minus, and this will give you 0. So they are orthogonal in this sense. Also, they are normalized. So if I compute the norm of this vector and the norm of this vector, I'll get 1. And what I said here is the following. As you do in linear algebra, I can write my vector in a given basis, which is E1 and E2, but I also can write the vector in a different basis. I can change the basis. And since plus and minus are vectors which are orthogonal and normalized, they are also a basis in the space of two entries vectors. Okay? So I can write C not as a linear combination of E1 and 2, but also as a linear combination of plus and minus. Okay? This is a property that follows from the fact that this is a basis. And when I do so I had before the vector expanded on the basis E1 and E2. But now I'm expanding the same vector. So this is a quantity, this is an object that has a meaning irrespective of the basis that I'm writing it, right? So I can expand this as the sum of these two vectors, but I can also expand it as the sum of these two objects. But I don't know what is the C1 and C2 values, so I have to compute. And in order to compute, I can just act with the bra plus on the ket theta. So you see that from this part of the equation, we're going to get C1, bra plus, ket plus, this is 1. And here you have C2, bra plus, ket minus. But bra plus, ket minus is 0. So when I act with a bra plus on the vector theta, I get C1. Okay? But since I'm expanding that in the basis E1 and E2, I will also get bra plus times ket E1 and bra plus ket E2. And the result of this scalar product is non-trivial. You have to compute. So what I wrote here was precisely the bra plus times the ket E1 times cosine plus E2 times sine, which is given by this vector. So when I compute now this number, so this scalar product, this will give a number, and the number is given here. So I know that when I expand theta on the basis of plus and minus, the coefficient of the plus cat will be this guy here. And I can repeat the same procedure for the minus vector. So if I act with the bra minus here, I will get the coefficient C2, which is 1 over square root of 2 e to the I theta. And therefore, I can just replace C1 and C2 by the coefficients that I just computed. C1 is given here, and C2 is given here. So I take this expression here, replace C1 by this, and I get this, and replace C2 by this, and I get this. So I'm saying that the vector theta can be written as a sum of circularly polarized states with these appropriate coefficients. Okay? So theta can either be written in this basis, E1 and E2, or in this basis, plus and minus. And the coefficients will be different. Okay? Because if I ask you what is the interpretation of the coefficient here, the coefficient of E1, when you expand theta, you know that the square of this coefficient will give to you the probability of getting the photons that were prepared on state theta in a state of polarization 0, because E1 is associated with polarization 0. And the coefficient here will tell you what the square of this coefficient will tell you what's the probability of getting a photon that was prepared with state theta in the state of polarization pi over 2. And now I can repeat the same thing for the circularly polarized. The coefficient here will tell you what is the probability of finding photons prepared with polarization theta in the plus circular polarized state. So you see that these coefficients here, 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 and here, they have different interpretations. So writing a vector in different bases will give you different information about the system. And let's say, the important part when you solve a problem in quantum mechanics is to find a suitable basis to expand your state in such a way that you get the result in an easy way. Okay? Sometimes expressing the state in a weird basis will not give you the information that you seek. Okay? And you have to do a very complicated calculation. But when you write the state vector in the appropriate basis that you want, sometimes reading off the probability is a piece of cake. Okay? Is that clearer now? Okay. 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 So, as I said, this is an entirely new way of thinking about how to extract physics of a system. So you should, if you're feeling confused, you should be. I mean, this is not a simple thing to get just as you see it. It's good if, I mean, of course, it is my task here is to say things that you understand, but after listening to that, you have to really digest those things and see if they make sense or not. And what I mean by they make sense or not is not if these things are intuitive or not. If it is the framework that I'm describing is, you know, a coherent picture of the description that is being proposed. Okay. Okay. So the next step that I want to discuss with you is the so-called projection operators that you already found in this lecture, which are those operators that we defined here as these big pies, okay? Pi is by definition what we call a projection operator. And you see that it is constructed out of the vectors that form the basis of your vector space, and you take the outer product between these vectors. Okay? This is different from the inner product, which gives you a number. Just to refresh your mind, the outer product between two vectors give you a 2 by 2 matrix if you're dealing with a two-level system. So these operators, they are called projection operators. So let us see how they come in. So you already know that a vector C can be expanded on the basis E1 and E2. And the coefficients that will appear here are nothing but the scalar product between the basis, the bra associated to the basis, and the vector itself. So the coefficient of E1 will be the bra E1 times C. And the coefficient of E2 will be the bra E2 times C. So these are just the coefficients of the expansion of the vector C on the basis E1 and E2. Okay? But now look at this expression here and look at this expression here. So just by the definition of the outer product that we gave a few slides ago, this guy, for instance, it can be written as E1, E1 acting on C, right? So remember, when you have an outer product, this bra will try to glue with this cat, so you form a scalar out of that, and then this will be a number. You can pull the number in front of the cat, and you're going to have this. Okay? So this is just the definition of the outer product. So this guy is nothing but E1 outer with E1 acting on C, right? But E1 outer product with E1, it is just, by definition, what we call pi 1. Okay? So this is a definition. And here, to write this as this form, I'm just using the definition of outer product. Okay? And you can repeat the same argument for E2. So E2, I can write as E2, E2, and this will be pi 2, acting on C. Okay? So, with this very simple observation, I am telling you that C, the vector C, can be written as pi 1 acting on C plus pi 2 acting on C, where pi 1 is this outer product of E1s, and pi 2 is this outer product of E2s. Okay? So you see that this guy here and this guy here, they will correspond to the component of the vector C in the basis E1 and 2. So pi 1 will give you the component of C in the direction E1, and pi 2 will give you the component of C in the direction E2. Okay, so it's like when you learn about vectors, so you have a vector V, and then you have the axis X and the axis Y. Now I can ask you, what is the component of the vector in the direction X? And you call this Vx, right? Here is the same. I'm writing a vector as the sum of two vectors. So here the component of the vector in the direction Y will be this one. And you can write that the vector V is the sum of Vx plus Vy. This follows just from basic vector algebra. And here I'm doing the same. I'm saying that C, which is the vector V, is the sum of a vector in one direction plus a vector in an orthogonal direction. And what pi 1 and pi 2 do for me, they project the vector in the corresponding orthogonal directions. So I can define a projector that acts on V and gives me Vx. In analogy here, I'm defining a projector that projects C in the direction E1. So this is the operator pi 1. And in analogy, you also define pi 2. So these pi operators, they are known as projection of the vector C on the direction Ej, if you are talking about pi j. And they obey a very important rule, which is the following. So, because I can write C as pi 1c plus pi 2c, and these are linear operators, we have discussed that, then I can write it as pi 1 plus pi 2 acting on C, which in compact notation is just the sum over j of pi j acting on C. But look, on the left-hand side of this equation, I have the vector C, and on the right-hand side, I have something acting on C. For this equation to be correct, this thing that appears here, which is nothing but the identity, so I'm multiplying the identity by the vector C, must be equal to the sum of the projection operators. Okay? So identity acting on C must be equal to the sum over the projections times C. Conclusion, the sum over projectors must be equal to the identity. Okay? So I'm saying that this quantity here should be equal to the identity. Okay? And you can actually show that explicitly by using an explicit choice of basis. Let me show to you that. Okay, so just to summarize, the sum over all projectors in a given vector space, and those projectors are by definition the outer product of the vectors that form the basis, they must give you the identity. This is what we often call the resolution of the identity. Okay? But let's see if this statement is true by an explicit example. Well, E1 outer E1 is 1, 0 column, 1, 0 row. Okay? This is the cat and this is the bra. You perform the product, you get this matrix. I invite you to do this calculation yourselves. Now you do the same with pi 2. You have the cat 0, 1 and the bra 0, 1. You compute the 2 by 2 matrix and you get this thing here. Now you sum them, because this is what this operation is telling you to do. Sum pi 1 and pi 2. And what you get is this matrix plus this matrix. So you have to sum the first entry with the first entry, the second entry with the second entry, and so on and so forth. So what you get when you sum this with this is the matrix 1, 0, 0, 1, which is nothing but the identity in the space of 2 by 2 matrices. Okay? So this is a very important relation, what I'm calling the resolution of the identity as being the sum over different projectors being the identity. We are going to use that all the time in quantum mechanics. Okay? So I think I will stop because you already learned a lot of material today. And what I'm going to discuss tomorrow is how is the form of an observable in quantum mechanics. And with this, you're going to learn how to compute the possible values of an observable in quantum mechanics. Okay? I understand that now the lectures are becoming a bit more spicy in the sense that you are dealing with more, mathematical language than previously. But please, I need you to ask questions, okay? Because quantum mechanics is not easy, and you learn that by practicing and by, trying to digest every concept, okay? Good. So tomorrow we continue, and if you have questions, specific questions about language, I mean, if there is some terminology that I'm using and you're not used to, just let me know, because then I can easily adapt what I'm saying or what I'm writing to you. Okay? So that's it. Thank you for your attention, and I see you tomorrow for the second lecture of this week. Okay, bye.